저희 콜로큐에 와주셔서 감사드리고요. 오늘의 연사님은 카이스트 김용경 교수님이십니다. 김용경 교수님은 99년에 위스콘신 메디슨에서 PhD를 받으셨고 그 후로 몇 군데 이제 위치에서 연구원으로 재직하셨습니다. 예를 들어 미네소타 경희 대학교 그리고 토론토 대학, 캘리포니아 주립대 리버사이드, and then so he has done couple of postdocships at UC Riverside, Toronto, and Yong University in Minnesota. And then he has begun his current faculty position at KAIST since 2005. Professor Kim is working on different topics such as reaction diffusion equations. His professor in biology, chemotactics, and diffusion, discontinuous diffusions, etc. I'd like to highlight one thing. So Professor Kim has solved a long-standing open problem, like for example, 160 years about heterogeneous diffusion. So his new model about the heterogeneous diffusion has been confirmed by experimental data recently. So that work has been recently published to Journal of American Society of Chemistry, which is the top prestigious journal in chemistry and maybe material science as well. So today, Professor Kim is going to talk about heterogeneous diffusion, mathematics in experiments. Please join me in welcoming Professor Kim.
Thank you very much. It's been quite a long time I've been here, and I'm very happy visiting postdoc again. Okay. So this talk is about the diffusion. So nowadays I'm mostly interested in the diffusion theory. So main thing is, I want to find the equation or model that explains diffusion phenomena better. And we mathematicians usually to work with some partial differential equation given by physicians, and then we just believe it, and then we do our best with believing that the equation is correct. But somehow I found, that's not exactly the case of the diffusion theory. So I thought, then what is the better diffusion model? So I thought about this on like 10 years. Now, if the environment is homogeneous, if everything is constant, then no problem. But when environment is heterogeneous, that means, here and there, different situation. Here, temperature is higher, here, temperature is lower. Or if here the material is A type, here, there are different kind of material. Then the diffusion environment is heterogeneous. So if it is heterogeneous, then the diffusion model is actually not correctly settled. So I thought about this for quite a long time. And then I'm going to show you some kind of also some experiment data. And then I want to explain this one. And in the data or in the experiment, there is some mathematics. So I want to talk about the mathematics in the experiment. So probably the second half of my talk is about this paper, very recent paper, since you mentioned about this. Now, in this paper is about the fractionation. Fractionation means, sometimes we start with the homogeneous or constant diffusivity of some particles or chemicals, but sometimes then, even if we start with the constant initial value, sometimes something happens, and in some area density increases, in some area density decreases. Then it becomes a non-constant steady state. Then we call this one fractionation. Somewhere more particles, somewhere less particles. So this paper is about the fractionation phenomena, but that one is by the heterogeneous diffusion. So experiment and the two-component random walk model. So the random diffusion model, what we are going to use it is a two-component coefficient. And then here the claim is, oh, we need two coefficients, not just one coefficient. We need two coefficients to explain diffusion. This paper is, okay, Ho Young Kim is my former PhD student. He got PhD like 2 years. And then now he's working in KAIST. And me, so, okay. Now experiment, Kunmin Lee, and the Myung-Chul Cho is his advisor. So, okay. Theoretically, okay, these two. Experimentally, these two are the main contributors. And here I want to talk about how we started this experiment. So this experiment is done by one of the laboratory in KAIST. And how do I know them? Okay, so when we do some joint work with the experiment people, the important role is not professor, graduate student. Okay, the reason, to me, okay, I know almost nobody in the university. I got a PhD somewhere else, and I moved here. And then, okay, I know the people in my department very well, but other department not. But graduate students like Ho Young Kim and probably most of students here have a lot of friends. And some friends are working in some laboratories or some other laboratory. So when I talk about this kind of phenomenon with Ho Young Kim, and then I mentioned, oh, it would be great if we have some experiment. Then, okay, then I definitely know I can explain this one using diffusion model. So suddenly he walked around some laboratory and found two places. So probably he visited like six places. He probably has enough friends, and then find two candidates, and then these two places are willing to do the experiment for us. Okay, and this is one of them. Okay, so here's the lesson is, okay, the professors here don't need to worry about the collaboration too much. Just ask your students to go around and find the place and specify what you want to do.
Well, how did your student know about this one before? I mean, he knew about this kind of a fraction
Sure. Yeah.
in math, but he or she is math or
Yeah. So Ho Young Kim is a PhD student in math, my student. So we already worked a couple of years, and then okay, at the time probably he already learned a lot about the diffusion theory and this kind of phenomenon he knows well. So he found the place.
What happens in the other candidates?
Oh, okay. So actually, I need one place is enough. And then this is okay. So I'm going to. So I think this is very good, important information when I give a talk here, post that. So we are also in a similar situation. So students very important, and they are very capable, a lot more capable than me. So. Okay, so my second half part, I'll talk about this one more. Then what is diffusion? You know what's the diffusion. Okay. So for example, here is the water, and then you put some diparticle here, and then if you stir it, it will be uniformly distributed eventually. But even if you don't stir, if you just wait enough time, then automatically it goes to equilibrium state that is diparticle uniformly distributed if you wait a long time. Why is that? Okay, we said that's the diffusion. Then what's the model for the diffusion phenomenon? How to explain this? So when we consider the diffusion model, the model, there are in two contexts. One is a physical model. So what is the physics behind this? Or we say, what is the mathematical model? So we want to write down the model using some mathematical equations. Okay, that's mathematical model. So usually what I think is usually people understand the physics first, and then they find the mathematical model using their physics. But the diffusion case, It was the opposite. It was different. Okay, so we know the physical model. Why is this? There is water molecules here. So water molecules are chaotic, moving chaotically, and they collide to the diparticle. Then the diparticle moves, gives some Brownian motion. Then this one gives eventually uniform distribution. And who made this theory? Einstein made this, 1905. 1905. Okay. But mathematical model, okay. So mathematical model comes actually from the heat conduction. So you need to understand the heat conduction first. So heat conduction, 1822, a lot earlier. Then Fourier proposed this kind of model, and heat flux is given like this. So if you look at this equation, the heat equation, then U, what is the U? Heat energy density. Heat energy is the U, the energy density. So, and K, conductivity, T, temperature. Okay, equation is given like this. Okay, so heat is moving from high energy place to low energy place. No, high temperature place to low temperature place. Okay, so temperature is somehow controls the movement of the heat energy. So that's the key. So okay, that one is this. Now in the homogeneous linear, what's a homogeneous linear heat conduction? So if C is the heat capacity, heat capacity, then heat energy U is integral of heat capacity from zero temperature to temperature T. So okay, this one is C times T. Of course, if you consider heterogeneous case, then this is C probably function of space. So here and here different material, then carrying capacity, heat capacity is different here and here. So C can be a function of S. And now here it's considered linear, but if temperature variation is large, probably there is non-linearity. So this heat capacity C may depend on the temperature itself, or this carrying capacity K may depend on the temperature itself. Then okay, it becomes more complicated. Okay. Now we have this. Okay, so it's a homogeneous linear case. Okay, U is this relation. Now temperature is U over C. Put that thing here. Then okay, you can get this. Now K and C constant. Then can take out. Then you can write this. So this is the heat equation. Simplest. Okay. Now okay, this one is by the Fourier, 1822. Now 1855. So 33 years after. Okay. The Fick found, we can use this theory to explain the diffusion phenomenon. Very natural, and his model is just D. So just consider D here. If this constant comes out, okay, D is not constant. Okay, what Fick considered is a homogeneous case only. So actually, D is constant. So basically, it's the same as the previous case. Then okay, then you can say, constant are the steady state of the phenomena. So, okay, we are happy. So you can say, okay, everything is spreaded, then these diparticles uniformly distributed, then, okay, so constant are steady states, then everything is fine. Okay. However, this is 1855, just 1 year later, Ludwig found that there were more salt particles in colder parts of the water. So if, okay, here is the cold part of the water, hot part of the water, then salt particles somehow placed on the cold place more, and hot, warm place less. So fractionation phenomenon was found. So, okay, people now think, if we have the fixed diffusion model, this cannot happen. This one should be uniformly distributed because here the steady state U equal constant. U equal constant is the steady state of this one. So okay, that's the fractionation phenomenon. Okay, then to explain this, what people do is, oh, this is the fixed diffusion. Okay, this is okay. We call this one is diffusivity of the fluid or fig. Okay, anyway, now put now temperature gradient term like this. Okay, and then if something is moving toward the temperature gradient, then okay, this coefficient should be negative. And against the temperature gradient, the cold place, then this coefficient should be positive, something like this. Okay, then you put this thing and fit the data, and then they think, okay, this explains this one a little bit, not perfectly, but a little bit. But still people puzzled. Where is this force, this term comes from? Okay, this is a little bit confusing. So, okay, there is a temperature gradient, then how come temperature pushes things? It's a little bit confusing, but people just take that and use this model to explain this. And then, but this does not explain what causes the fractionation. And sometimes people think, oh, is there a mysterious force driven by the temperature? What is that?
So what's the name of this model?
This model?
Yeah.
I don't know the name. So this one is a typical model for the heat thermal diffusion. Because thermal diffusion or thermal forests, we use this kind of name.
You really say that this is a model that explanation by this advection term, right?
Yeah. So basically, if there are some kind of this phenomena, then okay, we call this one phenomenological theory. If there is a phenomena, then okay, put the term. Okay. But this kind of phenomena actually appears many places. For example, if Keller's equation, biological pet, so you may consider bacteria or amoeba, they look like moving but very randomly. Okay, without knowing the information. Looks like they are moving some random movement, but somehow fractionation appears. Somewhere more bacteria, somewhere less. Somehow depending on the chemical food resource or some kind of chemical signal. Okay, why that happen? Then something happened here. Actually, it was online about it. When I saved this one. Okay, anyway. So what they do is, okay, if U is the density of bacteria of amoeba, what they do is, okay, fixed diffusion, and then put the gradient term. Okay, exactly the same way they explain. And then, okay, this chi is some chemosensitivity, and then they consider this. Then what is V? So when we talking about the Keller's equation, this V can be the chemical produced by the bacteria. Then okay, they use this model, the plus U minus V. If V is the food or resource they consume, then they use this model. So sometimes use this as an aggregation model. This one is called the consumption model, but the first equation is all the same. And what they do, oh, they move. Then okay, with the chemical, so not the temperature. Then okay, move this. Okay, so this is the model. So the concept is this. Oh, this is a bacteria. They're very tiny, but they somehow sense the chemical gradient. So they know where there are more or there are less. Then they, okay, depending on this, they can produce this kind of advection term. That's the theory of the Keller's, and that's what people believe for so long time. Question?
What are UNV? What do UNV represent? Is a population species.
Yeah. So in chemotaxis model, U is the population density of bacteria or amoeba or cells. And V is the density of some. So in the second case is V is some chemical or pheromone produced by the bacteria or amoeba. Or if the third one is V is the density of food, something. Or resource, sometimes the oxygen. Yep.
How can you relate from here to like U and B, their energy and temperature gradient?
V,
U and V are the two populations, right?
so U and V is two different things.
And they are in the original model,
Yeah.
energy and
Temperature. So
How can you relate this?
no. This is just an example. So in this model, U is the
Second term
U is the density of some chemical or salt. Now, okay, there is a temperature. Okay, temperature plays some role here. So here, probably not temperature, there is some chemical, if chemotaxis, whatever this. So you can forget the second two equations. So there is some chemical and gradient of chemical plays the same role of the gradient of the temperature in this theory. Okay.
So when this constant chi is positive, it means U moves in the direction where V is large, right?
Yeah. So if chi is positive, V is kind of, we call attractant.
Yeah.
Chi is negative in this model, then repellent. So something like that. Okay, so this one example. This I want to say is it is just an example. This is not my topic. There's another example. Okay, so in this example, people think, this is amoeba or bacteria. They are something alive, so they sense something, and the sensing makes this advection. That's the logic. Now here, okay, Dawkins experiment. So that's something like a AA size battery, and they put the metal bar, and there are two metal bars, and they are of different kind. The material is different. Okay, so they glue this one together. Okay, and then put this one in a very hot temperature, like I don't know, 1,000 Celsius, something like that. Then inside, here and here, there are carbon. So carbon is very important when you make the strong metal. If you have the poster here, you have the 포항제철.
Yeah.
Okay, that's a very important issue to them. So Dawkins did this experiment. So so probably in the beginning here, the carbon density in this metal was something like this, 0.5, a little bit less. On the right-hand side, a little bit above 0.5, something like this. But after waiting a long time, if you believe the fixed law, probably it should be homogenized, but it looks like separation. Okay, so this is another kind of a fractionation phenomenon.
But this left part is one inside one metal. The other part is the other metal, I see.
Yes. So this is metal A, this metal B. Okay, so two different type of the metal. Now here is the interface. Along the interface, okay, gap increases. Something like this. We call this fractionation. So this one said, some carbon is moving from here to this side.
Here, just temperature is to let carbon to move easily, right?
So temperature is very high, but no temperature gradient. Okay, temperature is same here, but important that okay, you want to observe this one not in 100 years later. You want to see in 10 days. Then okay, you have to put this one in a very hot temperature. Okay, 1,000 something. So that's what the people there are doing. Then how to explain this? You cannot put a temperature gradient, no. And this carbon, they are dead. They cannot sense anything. Okay. So what they do? They do is a chemical potential. Okay. Phi, put the gradient of chemical potential, and now explain this. But okay, if I give you these three examples, and actually there are more examples, and the point is fractionation appears in many places. And then all the explanation is something like this. Okay, now you start to do. Okay, is this good? Okay, my point look like, there is no correct way to understand the phenomena. So it happened, a fractionation happened, then put gradients or something, whatever it is. That's my feeling. And if I say this thing to the people who working in this, probably they are very mad at me. So I'm not going to do that. But these people nice to me. So we're mathematicians. Okay. Okay. So this is about. I took this picture from the Jung Kim's paper. So very recent one. So this is a cell. Okay, inside this single cell is small, but inside there is a chemical. Now the chemical somehow you can, if you look at this chemical, this one is the nucleus of the cell, and around here there are more chemicals, and here less. Sorry. So this look like fractionation phenomenon again. So it look like if the temperature is low, less fractionation. Temperature is high, okay, more fractionation. Now, microtubule, you know what's the microtubule? Microtubule is inside the cell, and they somehow make the shape of this. So it's not squashed. So microtubule is somehow this kind of lines, and then they can be used as the transport of some chemical, something like this. But if there are more microtube, there are more microtube, then less fractionation. If less microtube, then more fractionation somehow. Why is that? And then how to explain this one? So their model is, fixed law probably not good. So they use heterogeneous diffusion and then explain this one better. That's what they do. Of course, their work is influenced by me. We discuss about this kind of diffusion theory. So, okay, they picked up and then made this nice paper. So, but still people, okay, some people are not that dumb. So people try to understand the phenomena without using this kind of, to me, artificial advection term. Using just diffusion can explain the phenomena. So people do that. So fixed law is just this, then unique constant is the steady state. So everything goes to the constant state. So fractionation never happen here. So Chapman is the very famous one in mathematicians group. Chapman and Scott, he did a lot of things. And in this year, his purpose was to explain exactly this phenomenon. So he used the kinetic theory and then derived the diffusion equation. And what he derived is this. And Jung Kim also used this one. So Chapman's law. Okay. So if this is the case, now if the diffusivity depends on the temperature, you put this thing here, then you can rewrite this one here. So this one can explain, this thermal diffusion term may appear this kind of dynamics. Okay, so this is reasonable. So it's not artificial one. So basically, particles move just randomly, but if temperature is not constant, this one may naturally produce this term. So it's there is no hidden or mysterious force. This one is just a random movement. This one just comes from the random movement. Okay, so he derived that. 1905. So Einstein is 1905. So like 23 years later. Now, all right. Diffusion, okay, is 1914. Even 14 years before Chapman, he derived this one. I found this paper from Chapman's this paper. I tried to read this, but I could not find one. But anyway, that's one. Okay, but is this so? Remember name Wara. So we call this one Wara's law. We call this one Chapman's law. Okay.
So Chapman's law still assumes the temperature gradient. So without change of temperature over the space, T is constant, right?
T is constant.
Then okay.
Yeah. Okay.
That's maybe limitation.
So if T is constant, then everything is the same.
Yeah. Okay.
Okay. If T is not constant, then diffusivity may depend on the temperature. Higher temperature place, diffusivity is higher. Definitely. because they are moving more actively. Here, lower.
So Chapman's law still cannot explain the Darkin's experiment.
Oh,
Okay.
case of Darkin's experiment, D should depend on some chemical property.
Some other property.
Okay.
Some other property that it's quite complicated. So anyway, so this is the one. Now I call all these laws. So these laws are decided by the diffusivity only. Just one coefficient D decide the phenomena. And then I want to say, oh, probably not. Definitely not. We need something more. So this one is too much simplification. Okay, then which one should be the truth? Okay, now then to answer, I think this is a little bit opposite. Fick's law obtained 1855, and then Einstein 50 years later, okay, explained this one in a physical way. But after that, the theory should comes from this Einstein's idea for the heterogeneous case, but somehow it's still going to somehow influenced by the Fick's law. Of course, this Chapman's law is from the kinetic theory, but sometimes I say, okay, you have the kinetic theory, kinetic equation. Now you derive diffusion equation with the kinetic equation correctly, but that does not mean this diffusion equation is the correct one, because this kinetic equation is not that correct. Then okay, the result, even if the derivation is very correct, okay. Then what we have to do is look at the heterogeneous heat conduction a little bit closer. Okay, actually I already mentioned that. So this is the heat equation. Now important thing is temperature. Okay, heat flux is this. Now if you have the heterogeneity, then okay, K. So I think here the point what you want to see here is heterogeneity, not nonlinearity. Okay, there are sometimes people say, oh, mathematically, oh, heterogeneous one is still linear problem, so it's easy. Okay, math people probably prefer to have a nonlinear problem, a nonlinearity. But here, to explain this fractionation phenomena, heterogeneity is the one, not the nonlinearity. So I focus on the heterogeneity. So heat equation depends on the mode. Probably, if you consider heterogeneous case, then okay, this may depend on X. Carrying heat capacity may depending on space X. Okay, then if you derive, then okay, we have this relation. Put things here, then we have this. Now, if C of X, C is depending on X, this C cannot come out of this gradient. Okay, if this depending on space. Now, this one is also depending on space. So this one cannot go in or cannot go out. Okay, so it somehow stay like this. Okay. So what should be our question to have the correct diffusion equation? So the correct question is, what replaces temperature in the heat equation? In the heat conduction case, we use temperature. But diffusion case, something should replace T. Okay, we say call that P. Okay, what is the P? Now, you may think the temperature is something very well defined. No, temperature is also very tricky thing, and to define or to have the concept of temperature correctly, it takes a very, very long time. Okay, so but here the problem is the diffusion case, the corresponding quantity that controls the movement of the concentration or mass can be different each cases, so it's quite complicated. So not easy to answer. Or okay, but we have the heat capacity, something like this. Then okay, what should replace this? So instead of this, okay, put m of x. So there could be something else, and which cannot goes out, and this one, okay, is okay. Give the same name K, conductivity. So the more natural thing is that, okay, something should be here, something should be here. Homogeneous case, they are all constant, then comes out, but it's not the homogeneous that they stay in the correct place. Okay, that is the. So the natural one is, okay, if this is too much, then okay, this is simplified version. Now there are two components. Now we call this one two component diffusion law. Okay, so probably this is the correct approach if we compare with the diffusion equation. The previous one, okay, this one, they just try to explain everything in diffusivity D only. Probably that's not the correct way. Okay, so we call this one is a two-component diffusion law. Then question now, okay, if we use two components, can you do things better? Okay. So the short history of the temperature. Temperature was a hot issue at that time, long time ago. Wow, 증기기관 is a quite of the innovation, and that starts all this modern society. So temperature was very important, or heat very important. So 17, okay, Isaac Newton developed his temperature scale using linseed oil and setting. In the Newton's case, 0 is the freezing point of water, 12 is the body temperature. Now the body temperature 36, after they are different. Now, and okay, so after Newton, so Andreas Celsius introduced Celsius scale. So, but his scale is 0 is the boiling temperature. 100 is the freezing temperature. Okay, it's opposite. Now, after this one is changed. Now, temperature measured was complicated by many composite. Okay, so in this period of time, there are more than 35 kinds of temperature scale. And then, okay, John Dalton thinks that, okay, temperature, freezing temp, okay. 6,000 degree below freezing is probably the lowest temperature, something. Okay, so there are a lot of discussions. That one was big issue. So Kelvin's in this paper, somehow in his paper, somehow he defined, oh, temperature should be something, okay. Heat flux is given like this, then this one should be the temperature. So his definition is just taking the Fourier's law. Okay, so Fourier's law is 1822, and then take the Fourier's law, and okay, temperature is the one that satisfies that. That is the definition. More precise sentence is okay. If a unit of the heat transfer from object A, so transfer of the heat from temperature T to when two object is temperature T, this one is T minus 1. They come together, then heat moves, then the amount of the transfer should be same for any T. So that's exactly heat flux should be given by the gradient of the temperature. That should be the definition. Okay, so they return to, in my opinion, he just returned to the Fourier's law. So in our case, okay, we're using two coefficients, K and M, their product will be D. Then we want to know how they are decided. Then, okay, heat equation case, if there are two different materials, then okay, we can easily understand that conductivity are different if material is different, and carrying capacity is different if the material is different. But this diffusion case, it looks like that there is no different material, but it looks like only the movement of the particles are different here and here. And this one produce K and M. Actually, it's very hard to understand physically, but mathematically, we are better positioned. So here, the good point is physics people understand that this diffusivity is decided this kind of thing: particle velocity, turning frequency, collision time, viscosity of the fluid, or permeability, persistence, or moving rate, or walking distance. This kind of thing decide D, but they have the idea, but it's hard to see how this one decide K and M, which goes to the inside, which goes to the outside, which decide the steady. So if you look at, if you like this inside one M decide steady state. Steady state is M times U equal constant. So something decide the steady state, but something not. So this outside one decide the speed to arrive the steady state only, but not the steady state itself. M decide the steady state also. So here, okay, which makes K different, which make M different among all these things. So each of them has the contributions of K and M, and this is the example. Yes,
Yeah, I come with so this is we are talking about a diffusion case, right?
the diffusion case.
So what does K and M represent? It's
So
not conductivity K anymore, right?
yeah. So just copy this. This one is the heat equation case. Okay, now we just copy this one exactly here, and we now understand this one. We say this is the two-component diffusion law. So this case is different, but I use the same notation, K and conductivity. Okay. Now here's 1 over heat capacity. Now, okay, this one replaced by M. Okay, and I call this M motility. So some people call this one motility. So, okay. Thank you. Okay, so what we do is we consider a lot of random walk models. Okay. So random walk, the position, there are many kinds of random walk. So we call it the position jump or velocity jump or kinetic equation. There are many types. And in physics journal, there are also many papers related to the random walk models, like persistent random walk, or sometimes permeability things. Okay, there are many things. So, okay. Now, so here we actually consider many kinds of the random walk models. Okay, so for example, walk length is now every case we could only so our interest is the homogeneous case and heterogeneous case. Homogeneous case eventually all the same diffusion equation. Okay, the heterogeneous, so random walk. Okay, L is the walking distance, and then at each point the walking distance is different. Okay, so X dependency, that means the heterogeneity. Then this one, that K and M is somehow given like this. So some constant part take out, then L contribute to the K, L contribute to M equally.
When you say walk lengths,
Walk
it means you change your direction every this unit walk length size.
Yeah. So I do in a simpler way. So walk length, random walk is okay. I start from here, then one-dimensional case. I walk to here or here,
So
right?
the distance from here to next.
Yeah.
That is walk length.
That's the walk length. Okay, but here is okay. Let's mention about the reference point. I thought I would skip that part, but walk. It's a little bit complicated. So when I walk from here to here, I said this walking distance is given by position X. Yeah. Okay, so here and here walking distance can be different. Okay, at each position, there are corresponding walking distance, L of X. Now, when I walk from here and to here, then this is walking distance. Then this distance is given at what point? Here, starting point or ending point or middle point. So we have issue or somewhere. Okay. So the correct way, if I say, okay, look. So we talk about the reversibility. So walk on the right once and the left once, then you should return to the same position.
Yeah.
If you cannot arrive the same position, or you go further or less, then if you go right 100 times, left 100 times, then there are big difference. So this is not good. So I want to return to the same position. Okay. Then the walking distance, the reference point should be the middle point. So here, starting point, then okay, here walk here. And then here the arrow of x at that point is different, then probably you go less or more. Okay, so as walking length case reference point should be middle point, then you get this situation. Question.
Can you explain again why we have to make some reversibility?
Why? So if I go once to right and once to left, and if you do not return to the same position, okay, then you will have some serious advection. Okay, for example, go 100 steps there and 100 steps back, then probably there will be a lot difference. Then because of this difference, you will go somewhere else. So it's not completely the random movement. Okay, and that's the walking distance. This kind of issue it appears in the what stochastic problems. Okay, Ito integral. Ito integral is okay. You take the volatility from the starting point. Okay, Stratovich integral. Okay, that is taking in the middle point. Okay, so that's different. So okay. So this kind of issue, similar issue appears here and here. There.
By the way, if you use the other model, like just seeing origin or the end, how does that change?
Okay. So if you start the starting point, then this L goes inside here, and Chapman, you will get Chapman. Okay, and if you go to the arrival point, okay, then you will get fixed law. That's the Ninomiya's talk. No. Sorry. His case is different. His case is departing rate case. Okay. Now jumping time. Jumping time is okay. I walk every 1 second. That's a homogeneous case. But I walk every tau x time. So at position x, okay, you wait tau x amount and then walk. And there, okay, waiting time is a little bit different. Okay, then you have the heterogeneity. Then this one appears only m. Okay, but this one is very strange. If you take the reference point in the starting point or ending point or middle point, wherever you take the reference point, this one always appear here. It's quite different. Actually, it's very strange and amazing. So walk length, okay. Reference point make difference. Jumping time, reference point does not make a difference. Now departing rate, okay. Departing rate is the Ninomiya's talk. And then departing rate, okay. So not everybody leave. So at x, okay, only gamma x amount of the this is the rate. That amount of particles move. Well, that's the probability. Then that appears here. Okay, when reference point is starting point. And then I think departing rate case, taking the starting starting point sounds very reasonable. So that's Ito. Okay, so some people say, oh, Ito is correct. Some people say Sartor is correct. They somehow arguing, but it depends on what you are talking about. That should be distinguished. Oh, something like this. Now, you have a turning frequency. Turning frequency goes here. It does not make the difference in the steady state. And then this one is a speed. Okay, speed. Okay, it's a kinetic equation case. Okay, speed. Okay, goes here. Permeability always goes on K, and persistence goes into the K place. But interesting case here is if the persistence is not isotropic, anisotropic, then okay, M also changed. Okay, so this kind of thing. Okay, I talk too much. Okay, so I did not explain all of this. Yep.
So if underlying particles were like they are moving like random walks,
Yes.
but if they say for second case for each space, the jumping time is like governed by tau x. Then now if we average those, if we consider the density of the particles, then the density of the particles will follow the equation which whose K and M are given by like this.
Yeah.
And so this is mathematically done, or theoretical, or experimental.
So this one. Okay, so if we choose the middle point as the reference point, then we can show this. This one is proved. Now this one mathematically proved. So this one is not mathematically proved. So we have some estimation that it does not, it's independent of the jumping time. Okay, we have this kind of thing. But exactly this, okay, we have only one case. Complete proof is done by only one case that, okay, here is an interface, here is a different, and here tau x equal 1, here tau x equal 2. Here is the discontinuity. Then, okay, we prove that. So Mingi did this, something like this. And then not every, okay, but somehow departing rate case, so probably, so this one is actually known for a long time and probably proved by somebody. So I'm not going to make a paper with this. And okay, now this kind of thing is turning frequency. Okay, so this kind of thing, actually, we can observe it from the paper with some people, but formal derivation, not vigorous convergence thing, so something like this. Okay, so persistence case, okay, we this one probably I don't know, I don't know, but what we have is the convergence proof for the anisotropic case, so more than this. But not L2 convergence, L1 convergence, so it's with some restrictions, so not satisfactory, but something like this. So I want to show you some example. Then one of the things is kinetic equation. So okay, kinetic equation, we call this one velocity jump. Velocity jump. Not previously when I walked this one is called the position jump. This is more velocity jump. Velocity jump is a particle jumps from this velocity and to other velocity after collision. And then, okay, because of the velocity, if they are velocity, then they are moving. So you can find the position and then you can find the diffusion equation using that. So this is a typical one. Not typical one. This is very generous one, and we are considering this. Not everybody consider this. Now here is 1 over epsilon squared. So basically we are considering diffusion limit. When we consider diffusion limit, time t is order epsilon squared, and space is epsilon. So if we put that and then take the epsilon out and then divide the equation by epsilon squared to simplify, then we can arrange like this. So what is P? P is a particle density. Particle density at time t at position x. And there are many particles at x, but This is particle density with the velocity v. Now mu is turning frequency at position x, and for particle moving with the velocity v. Okay, probability to take the, so this one is probability to take velocity v. So v prime is the previous position. Now collision is happen at position x. Then okay, this one is the q is the probability to take the velocity v. Okay, now u is the density of the particles. So if you do the integration of this with respect to all the velocity, then okay, we can find the particle density at position x. Okay, so we do this. Now this q should satisfy certain condition, and the first condition is something like this. Okay, so at position x, this is the previous velocity. Now after the collision, this takes a v. Now if you integrate this one with respect to the new velocity, then that should be 1. Okay, that's for sure. So this one should take previous, whatever the previous velocity is, it should take one of the velocities. Okay, that's 1. But if you integrate this one with respect to v prime, not final one, the beginning, starting one, v prime, then that don't need to be 1. But many papers consider that case. That's their mistake. They should not do that. Okay, you may read some papers assuming this one and the integral with respect to v prime equal also 1. Okay, that's actually a uniform case. Okay, that's not. Now also we have this one. So this is the probability to take the v. Now this is the velocity. You multiply this, integrate this. Then if that one is not 0, that means that there is some advection done. So that one should be 0. Of course, it's not exactly the correct case. This one is the case when q is independent of v prime. If v prime, actually formula is not this. Not this, it's a little bit more complicated. Something like this is not enough. The integral, okay, with the v and v prime together, that should be 0, but it's not exactly true. Depending on mu, okay, the formula could be more complicated. But okay, this one is very simplified one, not exactly true, a little bit more complicated than this, but I did not want to mention that. Okay, now, so this, okay, now what usually people consider is the case that, okay, so here we have mu and q. So I already put the heterogeneity x here and x here. So mu and q are two places, two parameters. We can add some spatial heterogeneity. Most of the people don't consider the case. So most of the case, mu is independent of x, q is independent of x, but I want to consider x dependent. Now, mu, turning frequency. Okay, here I also consider the case mu depend on v, velocity. Okay, most of the people don't consider the case. I claim that's important. Turning frequency should depend on the velocity. Why? If some particle move very fast, it's more chance to collide. Move slowly, less chance. So it should depend on v. Okay? Okay, so actually we are working on this kind of case. But I cannot present this case. I present just the simplest case. Okay, mu is just function of x only. No v dependence. Now q is depending on just the final velocity. So no matter what the current velocity is, the probability to take the velocity v is the same. Okay, if there is no v, that means it's homogeneous or isotropic. If you have for different v, if it have a different probability, then you may have anisotropic diffusion. What is isotropic diffusion? What is anisotropic? Anisotropic diffusion means it depends on the direction. In this diffusivity in this direction and in this direction, that's different. Then we call this anisotropic diffusion. Then diffusivity D is not given by the scalar, given by a matrix. Okay, so that's anisotropic diffusion. So this is still anisotropic diffusion, but this is a simplified one. Okay, in this case, okay, this one is a formal derivation. And this formal derivation shows you diffusivity D only cannot explain this phenomena. We need two. And then, okay, this formal derivation, then this one is, I think, advantage of mathematics. Physics cannot see this. So, okay, so the previous one can be written like this in this simpler case. So means function of x only, so take out, okay, we write this. Now u is the integral of this. Now, okay, derivative integral of this one should be 1, okay. Then you can, this one can be somehow written like the simplified version or something like this. Now what you do is integrate this one with respect to v, then this one becomes u integral of this. Now, if you integral of this, so the integral of p, now integral of this, then the q is integral of q equal 1. So integral of this one is u, integral of this is u, cancel out. So right hand side equals 0. Now this one becomes this. So we call this one is a flux. Okay, so okay. Actually, this v is constant with respect to x, so you can take this one inside, then do the integration. Now you can rewrite this. The next part is multiply epsilon times v to this equation, and then we obtain this formula. Now v here multiply v, then okay, this one can be written like this. So v tensor product v, so this is a matrix. P, so this is matrix. So this is the gradient of the matrix. So notation of this one is not completely agreed with the people. So okay, but here the definition is okay. Here is the matrix. Then what is the gradient of the matrix? Then each row we take the divergence. Then we can get a vector. Then that's the meaning of this. And now we have this. Now to the integration. Okay, that is somehow integration gives the integration of this. Okay, we have this. Now this one, v integral v, we said this one equals 0. Without, so it's not 0, there is some advection, so this one should be 0. Now this becomes exactly flux. Okay, we have this one. Now we need two conditions. First, epsilon square term. So all of this one is formal derivation. Mathematically, what we have to prove is that, okay, we have to prove this one goes to 0, as epsilon goes to 0. Now we have here P of V. So P goes to some of this form, this one as epsilon goes to 0. We need proof, mathematical proof for this. If this one is done, then plug in to here, then we can obtain J like this. This is the flux. So if we have the flux, then you can see that one thing. P is somehow this. So intuitively, this one is clear. P is the density for particle with velocity v. So U is the everybody. Now this one is the probability to take the v. So this one should be proportional to this, right? So okay, put this thing in here, and this one equals 0. Then J is minus 1 over mu gradient of this inside. So there's this one is this. So this mu is function of x. Now this we have q. So somehow you can see that heterogeneity in q is inside. Heterogeneity of the mu outside. So it's separated. And if they are function of x, they cannot be combined. They should be, something should stay in the place of k, something should stay in the place of the m, something like this. So we can write this. So K and M, okay, so we have two components. Now this one is K and M is this one. So X, U is a function of X and T, so this can be out. So, okay, so we have like this, so this is that. So somehow, even before this, when we do the random position jump or this, somehow, oh, there should be something inside, something outside. That was very natural if you do the mathematical derivation. Yes, but that's actually something I don't understand. Why people consider just one diffusivity D only?
Was this hydrodynamic limit shown as formal computation, or someone prove it rigorously under simple assumptions?
So when I saw this one first is quite a long time ago by Thomas Hillen's paper. He has a formal derivation, not rigorous convergence. Okay, so this one is probably still the case, or somebody I don't know. But probably it's done. Our interest is not this. I think this is not the correct one. Okay. So the correct one is that, okay, this one, mu is not just dependent on x, but this one times speed. Speed, not the velocity, speed of v. That's important. Why? Then this one gives some kind of reversibility. Without that, no reversibility. Okay. Why is that? Okay, that's too much. So actually, you know, I was surprised that when I got the schedule, talk is from 3 to 5. So, oh, should I talk 2 hours? But these people may no problem with that. Yeah.
So in the kinetic equation, you assume did you assume any stochastic integral conventions?
No. So everything I do. So probably you do stochastic process. Do you work using no. Okay. So I didn't do that. So yeah. Having stochastic process to this one, probably that's an option, but I do everything deterministic way. That's who I am. And then here, these are the rates. So stochasticity somehow included in that way. It's what departing. This one is a collision rate. So something like this.
Related question is that can you get this? What is the relation between this one and random walk approach? Somehow you change this one over mu over x, say, and m, so that you can get also this random walk approach.
Position jump approach.
Yeah.
So
how do they relate to each other?
So you mean this? So if we do the position jump.
So here underlying particles are moving. At each position they follow some certain way, like walk length changes or something.
Yeah.
So this mu, one over mu or mu, and this or m or whatever, like, do they capture? If we say they equal to, like, say d0 times 1, 1 over tau of x or something, then somehow how do we know?
Actually, so here, what I did is to the heterogeneity for the random walk and the jumping time together. So these are together. Then we get here is rho here, L of x. Here we get L of x over tau of x. That's what we get. And so the relation, okay. So the relation of the position jump and this kinetic equation is actually giving you to me, the same equation.
Yes.
actually, but not this model. Not this model. This model is different. So if you look at here, you combine that, here what you have is L over tau. To me, that look like a velocity, V, a speed. You have speed. Here you have a rho, L only. Then, okay, so what is L? L is delta x. Then here one over mu. So mu is turning frequency. Turning frequency is like 1 over delta x or 1 over tau. So mu. So here look like I have here tau or delta t so here I have delta t. Then L is something like V times delta t. So mu is somehow 1 over mu appears actually here. Okay, but the point is, okay, so yeah, this is kind of amazing thing to me. So if you have a correct kinetic equation, not this, this is to me this is not correct. You have the formulate correct way for to have the reversibility. Basically, they give you the same thing. So in this case, what we have is inside here, you have V times V. Here we have V squared. We're here 1 over mu. So there are too much V here. 1 over the V should be placed outside to have the same result of the one. But this one is too much V. So this one is too much of the Chapman time. Okay, but so what we are trying to do nowadays is this. Mu is okay, some constant and multiply speed. Then that speed make a difference. Then that make 1 of velocity stay inside, 1 of the speed stay outside, and we get actually the same thing. And I never expected to talk about this one. This is quite a complicated thing. But okay. Second part, guys. It took too much time.
I think
Okay.
we can use the Q&A time for this part 2.
Yeah, so part 2 is simple.
Yeah, and then if you have a question, we can talk about it in the snack group after the Q&A session. Yeah.
Yeah. Actually, the second part probably more exciting because I'm going to talk about the ion battery modeling.
Ion battery, okay.
And then what we do is very related to that.
So what we are doing is very related to POSCO, actually.
POSCO ion battery?
Maybe.
Okay. The first part of this Dawkins experiment, ion bars. I thought that's POSCO. POSCO, but okay, yeah. So we do the experiment with the people there. So what this experiment is quite simple. Here is the 2 glass plate. Inside, what we put is acrylamide gel. So in this part, 12% of acrylamide and water. Here 4% acrylamide and water. So here more foam, here more soft. Okay, now we put dye particle inside. So my original plan was okay to put the dye particle uniformly everywhere. Okay, and I want to see the fractionation phenomenon. But when we make it here, okay, put some dye particle and 12% of acrylamide, and then okay, put this one first in this gap, and then let them solidify, and then put what is this? Put soft one first, okay. Then it takes more time to get solidified, and then put 12% later, and that gets solidified. But in the beginning, I hope to have the same amount of the dye particle density both sides. But experimentally, that's hard to obtain. There always is some difference. Okay. Then, okay, if we magnify this one somehow here is a 12%, then there are more acrylamide. So acrylamide, they make some kind of some links or this kind of shape. Now you have 4% acrylamide, so less, so it's more coarse, something like this. Then what we do is take the photo from above of this one, then we have the pictures. Now what we do is, okay, put this one and we take the photo at after 1 hour and 4 hours, 9, 16, something like this. We are taking the square of the time period. The reason is this is the property of diffusion. Okay, diffusion is what distance is related to the square of the time. So that's what we have. 1 hour shot. Okay, we throw it away. So it look like okay unstable, not stabilized yet. So becoming right after put this thing and then okay put this part here. That's hour 0. Wait 1 hour, probably not solidified yet, or initially a little bit different, or I don't know. So we throw it away and then we take these pictures. And what we do is, so this is the interface. So we take the average in vertical way. Okay, then we can obtain one-dimensional picture. Okay, this one is the picture. So the blue one is a 4-hour picture. And then after that goes up. Here goes down. Okay, you can really see the fractionation phenomenon. Okay, of course, when you look at this darken, they have two metals and more glued together with some technique. Actually, I wanted to do this kind of experiment with Jung in 정기연구원, and then okay. Yeah. But so somehow they cannot glue it. Probably function will be a lot to better. Okay. So interface was very sharp. Now here, when this one is solidified, probably there is some melted zone between. So it's not so sharp, but it looks like there is some period like this. And then really fractionation. So these physics people who do the experiment actually did not expect the fraction. Of course, I expect it, but they didn't. But so they surprised with this. Okay. So my idea is okay. I want to measure K and M. We can measure D diffusivity, and if we measure K and M, then okay, M is automatic. So if we measure 2, we have this. Okay, this one is porosity. So here, that's less porosity. Here, more porosity. Or permeability. I don't know how to understand the porosity and permeability. Here, permeability is less because that's more tangled. Permeability is better here. Porosity, okay. So what is the reason for this fractionation phenomenon? Is the diffusion alone responsible for it? Is another advection phenomenon involved? So that's the question, and our answer is there's no other advection. So diffusion alone is responsible for this phenomenon. Then how to explain that? So this one is okay. First we have the altogether 4% gel. Here this one 2%, 12% gel. Now measure the pattern. Okay, here to put here dye particle, 0 dye particle, and wait long time. Then they somewhat diffuse away and measure this pattern, and then you can estimate the diffusivity D.
Just K times M.
Not M. Yeah. M. D is K times M, and we measure diffusivity for 4% gel and 12% gel separately. Then we have D quite correctly. And then how about it's hard to measure K or M? Okay, so what we do is fitting. Okay, we have the data. Okay, we have the best M. Okay, if you find best M, then we have best K. Okay. So, and then we do the simulation and compare. Okay. And you may say, okay, we did the fitting. So this is our model. Now this is a fig. This one is the Warren. This is the Chapman. With blue dot, that's the pattern at our 4. Now we use this one as our initial value and then do the simulation with the, actually the domain the domain is bigger than this. So somehow, they're twice bigger than something like of this. And then, okay, reasonable boundary condition and do the simulation. Then you can see fit. Okay, gives you homogenization. Okay, this is not good. This one is fractionation or right model, too much. Chapman, too much. But we measured this one. So we have actually surprisingly close one. So this is the part we surprised. Now people say that, oh, you did the fitting, so you found you have 2 parameters, so definitely yours should be better. Definitely, I agree. So this one should be
The
better.
data 3 are just special cases of your model.
Yeah. So we have the 2 parameters, so better. But the point here is that this one is too close to this. And then you may think, oh, there is no other thing involved. This one is just enough. So that's the surprising part. Okay, so this is one of the experiment. Actually, at the time we had the 10 experiment. And then we have 10 pictures of this. And I thought that this one is the only good data. Others somehow mistake. No, others are also equally good. So this one is another data. So experiment guy forgot. Put here dye particle here. Put some dye here. On this region, they have to put some dye, but probably he forgot. He already put the dye, but he forgot and put dye one more time. So this one is a double of this. Okay, but anyway, initially probably the initial value something like this, and now blue is 4 o'clock, 4 hour, and now evolved like this. So this one was the data. So when he gave me this data, I thought, oh, it's failed, ruined. But no, if I use this one initial value like that and to the solve the equation, then you get this. Oh, surprisingly close. So if you look at this, then probably you will lose the 의심. No more 의심. Okay.
So it seems there are many different states depending on
Initial.
which initial dye distribution.
Yeah.
How did you
No,
model this?
Oh, sorry. So actually, this one is evolves something like, if it wait longer time, this one will go something like this. This one will go something like this. So basically, this shape is exactly same as this shape eventually. Yeah.
Sorry. So this curve you showed is not the steady state.
I say not the steady state. This one is evolving, and they will basically give the same time of the steady state. Of course, here there are too much part chemical here, so steady state is around the 90, and but a little bit of the fractionation. A question?
No, I mean.
What's this? Okay. Yeah.
I'm sorry, but confusing. What is fitting parameter for your equation?
So we have a K and okay, so we have D. D is measured one, diffusivity D. So D is K times M. So we need one of them. So we use M as a fitting parameter. Or which is M, use K or M as a fitting parameter. So we have the data and we find the best M. And best M, okay, we take the best M, then we have this pattern.
So you have D for 12% and D for 4%.
Yeah.
And your free parameter is M for 12% and M for 4%.
Yeah. But also, there is a, okay, so So you have K and M, okay? Now if you multiply constant, any constant to K, then multiply 1 over the constant to M, that's it, nothing changed. So in that case, there is some freedom of some constant. So what I do is, okay, you can do M here, 1. And M only, this one is the parameter we need to find. Okay, that's what it is. Now this is other ones. Oh, so this one is a little bit different setting, but somehow this one was our initial value. Why this happened? We have the story. So sometimes they accidentally put the low density one later. Then it took a longer time to get solidified. Then okay, somehow they give this kind of pattern at 4 o'clock, 4 hour, and then that evolved something like this. I thought this one was a failure. No. Even this case, you start with this initial value to solve it. Okay, somehow you can see, how can it say different? They are different. How can it say there should be another dynamics? No, this one is just enough. This one is some other case. So take the initial value like this, okay, observation. Now we see this. Okay, so actually this experiment lab professor wants to advertise this one. So okay, we will say, oh, 160-year-old problem is solved, something like this. So what is the problem? That is, oh, our conclusion, diffusion is the sole cause for this fractionation. Any additional advection dynamic does not exist, for at least in our experiment. And we believe that should be the same case in many other fractionation phenomena. So, okay, this one is the, okay, we say, okay, this one is the solution. Application of two component diffusion law. So, actually, the examples we showed in previously chemotaxis model, we can use this model, this one, that we may obtain better chemotaxis model. And that's what we did actually quite along with Yong. Yes.
Do you fix that the 12% and 4% all the time?
Oh, no. Okay. So if you look at this, so this one is we did several different cases. So there are we use 2 types of the dye particles. And this is another kind, different kind of dye particle of the previous one. Now this is 12%, 4%. This one is 5% to 10%. Okay, so we also use a different type. This is different type of the dye particle. Now if you look at here, this 12% is on the left, 4% on the right. Now this one is actually opposite. Now usually higher density acrylamide should be on the left-hand side. Okay, so all of them are case, but this one is mistake. Okay, and anyway, we get the case. Okay, so when we consider the metal thing, or we can chemotaxis, also chemotaxis model, we use actually this kind of diffusion model to explain phenomena without putting the artificial or chemotaxis term. Then even though this model naturally gives you some chemotaxis thing, and then this one is actually easier for the analysis. We did this. But lithium battery is probably the next topic I'm going to do. So, okay, I ask now. Now I am new graduate student. Now I learned something from the previous experiment. So ask them, oh, go and find your friend in some laboratory doing lithium battery. Okay, and then do some discussion, and then okay, find something we can do together. Okay, so they have some many friends over there. Okay, I think that's a very good way, or that's the right way we do the collaboration with the experiment people, and that was very nice. So this one is a battery thing. So how did this one is made? Then if you look at this, when I look at that, that one is very close to our experiment. So here there is a what liquid. Then the battery here is a cathode. Cathode is plus. Anode, that is the minus probably. And then there is a separator here. And here they put lithium metal, but they are not just one solid metal, probably they are somehow grounded. I don't know how they made this, but there's a liquid and the liquid is inside here. So, okay. Now here, graphene or something graphite or graphene thing. Then, okay, this one is here. Then, if you take the electron out and take out, then lithium becomes an ion and melted in the liquid. Okay, and then okay, they are melted there. What they do? They diffuse. So that's the diffusion. Now here is a separator. Then the lithium ion goes through here. Okay. Now if you go there, and then if you get the electron here together, they combine, then they somehow grounded in this side. So if a lot of lithium ion comes here, that means that this one is fully charged. Okay, and then but this lithium ion, they are not moving toward this. No reason. What they do is just a diffusion, nothing else. Okay, and then okay, if this one is fully charged, then okay, use the battery. Then using the battery means the electron goes here. Then it's combined with the lithium ion around this area. Okay, then this one becomes grounded in this side. Then okay, then there are more rooms that particle lithium ion goes here. So this one is exactly diffusion phenomenon. So outside movement of the electrons.
I'm also not knowledgeable about battery, but isn't lithium should also move by potential difference, something electric potential difference or something?
Yeah. So their theory, the theory is electrons move with this according to this electron rules, and this one is moving with diffusion. Okay, that's the current theory. Okay. This is funny. Let me say it works. Okay, now this one is some web page. Okay, this is the way they explain. This one is just moving directly, but it's not the case. It's a more diffusion phenomena. And okay, and they go there. Okay. Then what people use this kind of model? There's a fixed law and the source. This source term is somehow explained, okay, various way. So this source term somehow explains the case, electrons coming out, then lithium ion is produced there. If electron is combined, then lithium ion disappears there. So that is what this one means. I just copied from some paper. I don't but here the point is they are using this fixed law. But if you look at the material inside of this, then there are two types of the materials here. The epsilon over there is porosity. And because of different porosity, so how to explain the phenomena of the diffusion using this diffusion law? But we know that, okay, if we use two-component law, then it will be better, definitely. And also, if you look at this one, they say one of the main issue is the production of the heat. Then heat also changed this diffusion phenomena. So we can include we can include the heat change or heat production in the model better. Then it looks like there are too much rooms we can improve the model. So okay. So we have a lot of room to contribute to this model if we have a diffusion model better. Okay, that's it. Thank you very much.
Before the time limitation, let us get a couple of quick questions. Any questions?
So
Sorry.
so in your model, if the K and M are just not discontinuous piecewise constant, then I think this fractionation is just natural phenomenon. You, as a steady solution, you get this phenomenon, right?
Yeah. So if it's piecewise constant, then you can very clearly see the fractionation. So fractionation will be very sharp along the interface. But most of the cases, okay, the change is gradual, and then fractionation is also gradual.
And give me a second. Yeah, go ahead.
Yes. In the previous slide about the experiment, you say that there is no advection term, and we
actually, we have no extra advection. So we have only diffusion. But if you rewrite the diffusion, then you can split it into two parts. Then because of that, you may have some extra advection term. Okay, but the point here is this one is produced by the diffusion or random movement only.
but you fit the K and M,
Then
is there any difference with the phenomenological advection term in the former slide, like Duncan's experiment or any other phenomenological advection term?
Okay. So here the point is when I talk about this kind of experiment, this one, for example, this. Talk about this one with some material science people in Yong when I went there. They know the model using this chemical potential. But what the model gives you is a steady state. Okay, so you start from here, okay, put this, then, okay. Basically, the model is to fit the steady state. Then, okay, for example, make this chemical potential appropriately to the potential steady state. And they say, oh, and then they, 오늘 뭐라고 그래야 돼? 그냥 퉁쳐서 퉁친다. 그래서 so eventually they only explain the steady state. But what they surprised here is this one explains the dynamics, how they evolve to the steady state. Okay, so the model, that model, and this model is completely different, and you can see the dynamics, not just the steady state dynamics.
Then K and M fixed with the time.
Yeah, K and M is fixed with time.
They are constant for the same material, 12% and 4%.
Maybe last question.
So you show that K and M may originates from various microscopic picture like random sum vision. And let's say we measured K and M from experiment. And can we go further? Can we distinguish such microscopic pictures? Or are they equivalent?
Okay. So experimentally, what we did is forget about the theory, forget about what is the walk length or jumping rate or whatever. We forget about everything. What we take is just two coefficient diffusion law, and then fit the coefficient there with the experiment data. Then okay, this explains things perfectly, in my opinion. Something like this is perfect. Okay. Now your question is, can we connect this kind of model or this kind of parameter using this random walk idea? Okay, so that's a very natural question, and of course we consider that. So actually, what we do, okay, what we can write is this one. Equation is UT divergence K gradient of M. Okay, and we have this. And I told you, if we multiply some constant here, then divide here with the constant, that's all the same. So there is no unique way to write this. Now, the effect of K and M. Effect of K and M. So we have also rewrite this one. Something like this, D 1 minus Q gradient D Q U. We can also rewrite this one like this. Now here Q is also now function of X. Okay, Q is function of XD. So instead of K and M, so we rewrite this. If we rewrite this, then we can see, oh, which one plays the bigger role, M or K? Now if we write like this, so if Q equals 0, that's a fixed law. If Q is small, that means, okay, this plays a bigger role. Q is large, or up to 1, then okay, M plays the bigger role. So you can say this kind of thing. Okay? Okay, that's one thing. So if we look at this, our explanation, our model, is this acrylamide. That one is more related to, a little bit related to the walk length. Okay, so if you have the coarse one, then probably you may think random walk is bigger here, smaller here. And also, that one plays a role of the permeability. If this one is tangled a lot, then permeability is bad. Otherwise, permeability is bigger. But you can see the permeability plays the role in K only. Okay, so this experiment itself, if you look at that, look like because of the permeability, probably the variation of K will be bigger than M. So in this case, we will actually find the Q. Q is about 1/4 the experiment data. That means, oh, this one plays a little bit bigger role because of this permeability thing. So it looks very reasonable. Okay, and also you can do some computation. Here is 12%. Here is 4%. Now you may measure the walk length. So walk length. Then okay, actually it's some people say, okay, since this one is a two-dimensional one, so walk length should be here proportional to the square root of 12 and square root of 4. Oh, okay. Wow, basically this one is a 3-dimension. Should we call it a 3-dimension? Then the cubed root of cubed root. So we compare walk length using that information, and then also consider some permeability issue. then somehow this kind of parameters somehow reasonably explains this one. So, but I don't give too much credit for this kind of analysis. But in the paper, we have this kind of discussion a lot, and the physics people like that discussion a lot. So okay, but I don't buy too much, but we have this kind of one, and so that's a good point of this good point of this model, connecting parameters and random parameters.
Okay, so I think you guys can keep discussing with the speaker at the snack room. So please thank the speaker again.